Now we will try and build a common source amplifier using a PMOS transistor. For illustration, I will use a PMOS transistor whose mu PCox product is 25 microampere per volt square, and I will choose W by L equals 4. So what this does is to have mu PCox W by L equals 100 microampere per volt square, the same as for the NMOS transistor. So this is just convenient, so we can use the results that we already calculated and so on. And I'll also assume that the threshold voltage of the PMOS transistor is 1 volt, again the same as NMOS transistor. But please do keep in mind that mu PCox and mu Cox will be different, and they may not be in this exact ratio 1 to 4. And also this W by L, if you're designing an integrated circuit, is variable. Okay, you can have W by Ls which are very small, like 1 or something, and you can have thousands and even 10,000s and so on. Okay, but we'll use these parameters for estimation. Of course, for any other value of W by L, you should be able to calculate the parameters quite easily. And I will assume that the GM I need is 200 microsiemens. So if you calculate with this Kn of 100 microampere per volt square and VTP of 1 volt, you will find that the source gate voltage has to be 3 volts. Okay, and the source drain voltage has to be greater than or equal to 2 volts for it to remain in saturation region. Okay, just as with NMOS, because now voltages will be defined the other way, don't get confused. Just like with NMOS, if this voltage, if the difference between this and that becomes very small, that is, if the difference tends to get squeezed, then it goes into triode region. If the difference is large, it will be in saturation region. You can calculate the exact values. In case of NMOS, the drain voltage can go below the gate voltage, but not by more than 1 threshold voltage. In case of PMOS, the drain voltage can go above the gate voltage, but not by more than 1 threshold voltage. Okay, so that's what the saturation condition means. The first step is to bias it. Just like with the NMOS transistor, we use constant VGS biasing just for illustration. Okay, so we want VSG equals 3 volts. So I'll use 3 volts here, and we want VSD of some value. So let me assume that it is 4 volts. So this will set up the operating point of the transistor in the saturation region. Okay, VSD equals 4 volts and VSG equals 3 volts, and clearly VSD is more than VSG minus VT. Okay, now this is how you set up the operating point. And let me imagine that the small signal picture of the common source amplifier is like this. I have some input source Vi, and just for illustration, initially I will assume that there is no source resistance Rs. So Vi will be applied as VGS to the MOS transistor. We have the control source GM VGS, and we will have the load resistor RL. And just like before, from our experience, we know that there could be an extra resistance here for the sake of biasing, and there could also be extra resistances here for the sake of biasing. Okay, so now the question is how to combine this signal picture with this operating point picture. Okay, we've already gone through this, so that's why I'm going to go a little quick, but you should be able to again follow the same logic that we did with the NMOS common source amplifier. I'll also show RD because we're going to use it anyway. This is GM VGS and this is VGS. Okay. Now remember, RD is what we use for biasing on the drain side, and RL is the load we AC couple to the common source amplifier. We have already learnt all these things, so we are going to use them. We know them and we'll use them. Okay. So first, let me show this VSG of 3 volts and the PMOS transistor. Okay. And to bias on the drain side, we'll have this RD. Okay. And let me imagine that this is 100 kilo ohm, and I have to connect the supply voltage. I'll still call it VDD like that. Okay. Now we know that for VSD equals 3 volts, the drain current of the MOS transistor will be 200 microamperes, and this will be 20 volts, and we wanted 4 volts across the MOS transistor, so this VDD will be 24 volts. Okay. Now like before, I don't want to use 2 separate DC sources. We know what to do. This is also generated from the higher source VDD using a voltage divider. Okay. Again, because we know all this, I'll go quickly through these things. So I'll use a voltage divider across the supply, and this will provide the source gate voltage bias. This is VSG. Let me call this R2 and this R1. Then the voltage VSG is nothing but VDD times R2 by R1 plus R2, because this VSG is across R2. Okay. So we can adjust the ratio R2 by R1 plus R2 to be the appropriate value, so that we get 3 volts. That's quite easy. Okay. For instance, I could pick R1 to be 21 mega ohm and R2 to be 3 mega ohm, and I'll get 3 volts across this. Okay. In this circuit, the operating point is established. We have a source drain voltage of 4 volts and a source gate voltage of 3 volts. And we have to add the input voltage and also connect the load resistance. How do we add the input? It's the usual AC coupling stuff. We have VI and connect a capacitor C1 to couple it, so that if you choose C1 to be sufficiently large, at this point you will get the quiescent gate voltage plus the input voltage. The input voltage will get added to it. Okay. Similarly, the load resistance RL, which has to be ground reference, that is, its one terminal has to be ground, is AC coupled to the drain of the transistor. Okay. This is C2. Okay. And so far I have not shown the ground for this supply voltage. In case of the NMOS transistor circuit, we had grounded the source of the MOS transistor, that is even in the operating point picture. Okay. So we had this as ground, and this is perfectly possible. If we call this ground, this point will be at minus 24 volts, and there are many circuits which do work with negative supply voltages. Okay. But in case of integrated circuits and these MOS circuits in general, it is common to use the negative side of this voltage supply as ground, so that you think of the circuit as being operated with a positive supply voltage. So this side is ground, and this is quite common whenever you have a single supply. It's not a rule, but it is quite common. Okay. So when you have a single supply, you think of this bottom rail as ground and the upper rail as the supply voltage. There are exceptions to this. Sometimes you do have circuits which run off a negative voltage, but most of the time this is what we do. Okay. So we'll still call this the ground, the bottom side, and this upper rail will still be at 24 volts. Okay. Now as far as incremental picture is concerned, this and this are both at ground. Okay. And this RL, it's connected to the common reference node of the circuit, which is ground, which is on this side. Okay. So that's the complete PMOS common source amplifier. Okay. I have Vi and I AC couple it to this point, which is the gate, and I have AC coupled the load to the drain. Okay. Only thing is, note that the voltage here is not the source gate voltage. The source gate voltage is the voltage between these 2 points. Okay. Don't get confused by that. But otherwise, things are the same. Okay. The small signal picture of this will be exactly the same as before. Yeah, again, as I mentioned, this side is what is grounded. Okay. In the NMOS case, the source of the MOS transistor was the common reference node, and in this case the common reference node is towards the drain side. Okay. This is because we prefer to operate with positive supply voltages. Okay. This is the reference node or ground. Okay. Now if you draw the incremental picture of this, we'll have Vi, and I'll still show C1. By the way, just for simplicity, I didn't show the internal resistance of this source Vi, but actually I can add it. It is not very difficult to include. So I'll have Rs over there. So that means I'll have Rs over here. Okay. And as far as the MOS transistor is concerned, nothing has changed. Okay. So this point is the gate, and that is the gate. And from gate to ground, we have R1 parallel R2, because we have R1 over here and R2 there, and this point is also incremental ground. Okay. This is R1 parallel R2. Then we have Gm times VGS. Okay. Remember, the small signal model of the PMOS is exactly same as that of the NMOS when we write it in terms of VGS. And then we have RD from drain to ground, we have C2 and RL. Okay. So this is the incremental picture of the PMOS common source amplifier, and you can see that it is exactly the same as that of the NMOS common source amplifier. And also, if the PMOS transistor has non-zero lambda, it will have a non-zero output conductance, and that is included over there. Okay. As usual, it just appears in parallel with RD and RL. Okay. So as far as the small signal picture or the incremental picture is concerned, everything is exactly the same between PMOS and NMOS cases. It's the operating point and some other large signal characteristics that will be different. We'll see what they are. Okay. Now we want C1 and C2 to be shorts, and we have done this so many times that I will run through it. For C1 to be a short, its reactance has to be much smaller than the resistance that appears across it when the source is reduced to 0. Source is reduced to 0, we have Rs and this resistance. Okay. So the reactance of the capacitor C1, 1 over omega C1, must be much smaller than Rs plus R1 parallel R2, or this means that C1 has to be much more than 1 over omega times Rs plus R1 parallel R2. Okay. Now on the output side, exactly the same thing holds, and I'll as usual ignore this GDS, but if it is there, it just appears in parallel with RD. The reactance of this capacitor C2 has to be much smaller than the resistance that appears across it, which is Rd plus RL. Okay. So 1 over omega C2 is much smaller than Rd plus RL. Okay. Or C2 has to be much greater than 1 over omega times Rd plus RL. But we also discussed earlier that this is the condition that makes sure that the voltage at the output is the same whether you have C2 or if it is really short circuited. This constraint will make sure of that. But sometimes we also need an additional constraint, especially if the value of Rd is very high. We want this voltage and that voltage to be the same. Okay, from the discussion on swing limits, you know that what limits the swing is the voltage at the drain, not the output voltage. Okay, so if Rd is very large, you could end up in a situation where the voltage swing here is larger than the output voltage. If you have that, what it means is that the transistor will go into saturation for a smaller output voltage than you originally thought. Okay, so that's why we want the drain voltage to be the same as the output voltage, and the condition for that is omega C2 has to be much smaller than RL, or C2 has to be much greater than 1 over omega RL. Okay, and once these conditions are satisfied, the capacitors do behave like short circuits. Okay, so that's the picture we have, and we can easily see that V naught by Vi will be minus Gm times Rd parallel RL times the voltage division due to the source resistance R1 parallel R2 divided by Rs plus R1 parallel R2. Okay, and if you do choose R1 parallel R2 to be much greater than Rs, this whole thing will reduce to minus Gm Rd parallel RL. Okay, so the small signal picture wise nothing is different. I just went through it and it's exactly the same as in the NMOS common source amplifier. Okay, now what is really different between PMOS and NMOS stuff we'll see in the following lessons. Okay.